All right, so now we're going to move into some properties of sets and some operations on sets. So let's start with the cardinal number of a set S. We're going to denote that with n of S. Think n for number of elements in the set S, okay? S is finite if n of S is 0 or a natural number. Otherwise, we say that the set S is infinite. So let's look at an example here. Let's start with the set K, and let's determine its cardinality. So K consists of the elements 3, 5, 8, 0, 11, and we're just going to count the number of elements in here. So I have 1, 2, 3, 4, 5. So that means that n of K is 5. Let's move to the right over here. L is the set containing 0. How many things are in set L? Well, there's just one thing, right? 0. So n of L is 1. X is the set of all x, such that x is a real number and x equals x plus 1. Well, let's think about what it means for x to equal x plus 1. Well, if I tried to solve this, I would say subtract x from both sides. And I would get a statement that says 0 equals 1. But that's not true. So what that means is there's no solutions to the equation x equals x plus 1. So that means that x is empty. The big set x is empty. It has no elements. So what is n of x? Well, there's nothing in there. So, whoops. What happened there? N of x is 0. Let's see if we can get that back. There we go. All right, what about y equal to this funny looking 0 with a line through it? This notation means the empty set. Now, sometimes you'll see it more ovally like a 0. Sometimes it's just a circle with a line through it. But this is the empty set. That's exactly what x was here. X is empty. It's also the empty set. So what is n of y? N of y is 0. And there's nothing in y. All right. Well, let me erase my notations so you can read this. Let's think about the sets here and determine if each is finite or infinite. So let's start with the set of U.S. presidents. So how many presidents have we had? Have we had a finite number of presidents or an infinite number of presidents? Well, we've had a finite number of presidents, right? We could find the number of presidents. In fact, what is President Trump is he the 45th or 46th president? I'm going to Google it real fast. He's the 45th, right? President and the 44th person to hold the job. Okay, so the set of U.S. presidents is finite. Let's look at B, the set of natural numbers. So remember, the set of natural numbers is the set n. I'm going to write up here at the top n, starting with 1. So 1, 2, 3, 4, and so on. That dot, dot, dot means it keeps going like that. Is that going to be finite or infinite? That's going to be infinite. What about A equal to the set of n greater than 5 such that n is a natural number? Well, what's A going to look like? I'm going to write here on the side. A, well, it has to be natural numbers that are bigger than 5. So the first element here is going to be 6, but then 7, 8, 9, and so on. Is that going to be finite or infinite? Going to be infinite. And finally, what about B equal to set of n less than or equal to 5 such that n is a natural number? Well, here, what lives in B? Well, there's 1, 2, 3, 4, and 5. So is that infinite or finite? Well, we can count the numbers here. There are 5 numbers, so that's finite. Okay. All right, so when we're dealing with sets, we want to think of a universal set as sort of the larger set in which all of the sets we're talking about live. Okay, so here I'm going to let my universal set be U. So I'm living in the universe of U.S. senators, U. And I want to think about the members of the universal set U who are females. Okay, so I'm thinking about just the set of female U.S. senators. This set is contained in U, but it does not contain all of the members of U. So we could denote this set here in set builder notation. F is the set of X, such that X is a female U.S. senator. If I wanted to draw a picture, this is called a Venn diagram. Here is a picture of what our set looks like. U is the outside rectangle. And so we'll always use a rectangle like this to denote our universe. And then F is this red circle, and that's the set of all female U.S. senators. Okay, so a Venn diagram is just a picture that describes the sets inside a universe. The complement of a set, this is an important definition. The complement is the set of elements in your universe that are not in the given set you're looking at. So if we're looking at the complement here of F, where F is the set of female U.S. senators, the complement is everything outside of F. Whoops. So the shaded green part is F complement, and we denote that with a bar over it. Okay, so that's everything outside of F in my universe. In general, the complement of a set A is denoted with an A with a bar over it, and it's the set of X in the universe such that X is not in A. So when you see the notation A bar, what you should think is not A. Okay. All right, so let's try finding some examples here. If my universe is the set containing A, B, C, D, so I live in the land of just A, B, C, D, and B is the set containing C, D, let's find the following complement. So let's start with B complement. So B complement is everything in U that's not in B. Well, I just go through the elements of U and decide is it in B or not. So A is not in B, so that's going to go in B complement. B is not in B, so that's going to go in B complement. And the remaining elements of U, C and D, both live in B, so that's it. Okay, so B complement is just the set containing A and B. What about U complement? Well, U complement is the set of everything in U that's not in U. Now, it sounds a little funny to say. There's nothing in U that's not in U, right? Everything in U is in U. So U complement is the empty set. Right. What about the complement of the empty set? Well, the complement of the empty set is everything in U that is not in the empty set. Well, everything in U is not in the empty set. So here, this is going to be A, B, C, and D, which is exactly U. In general, in any problem, U complement will always be the empty set, and the empty set complement will always be U. Let's look at B. U is going to be the set of all X, such that X is an animal in the zoo, and S is a set of all X, such that X is a snake in the zoo. What is S complement? Well, here it's going to be hard for me to actually list out the elements of S complement, and that's why we're asked to just describe S complement. So S complement is going to be the set of all X such that, well, X has to live in U and not in S. Right? Well, what does that mean? It means that X is an animal in the zoo. That's what it means to live in U. But it can't be a snake, right? So, and is not a snake. All right. Let's look at C. If U is the set of natural numbers, E is the set 2, 4, 6, 8, and so on, so the set of even natural numbers. And O is the set 1, 3, 5, 7, and so on, so the set of odd natural numbers. Find E complement and O complement. So let's start with E complement. So E complement, we should think not E. So not E, if E is the set of evens, we're looking for not evens that live in the natural numbers. That's exactly the set of odds, right? 1, 3, 5, 7, and so on. That's just O. Similarly, if I look at O complement, I'm thinking about not O, or the not odd numbers. Well, if you're not odd, then you must be even. So that's going to have 2, 4, 6, 8, and so on. That's exactly my set E. Whoops, not with a bar. Okay. All right, so that's the complement. Let's look at subsets. We say that B is a subset of A, written with this funny looking sort of cup symbol with a line under it. So B is a subset of A if and only if every element of B is an element of A. If B is a subset of A but B is not equal to A, we call B a proper subset of A, and we drop that little line underneath. So that line underneath is telling you it's a subset of A, or it could be equal to A. But if you're equal, you're also a subset. When a set B is not a subset of another set, we just draw a slash through our subset symbol. All right, so let's think about set relationships between the sets given here on the bottom of your screen. So my universe is the set of numbers 1 through 10, and we're just going to look at these sets. What I'd like you to do is pause the video and think a little bit yourself about some relationships, and then I'll talk through some relationships. I won't list them all here, so if I don't list something that you listed, you should ask about it in class, okay? But go ahead and pause for a second and then come back. All right, so hopefully you've thought about this for a minute. Let's think about what set relationships we have. Well, the empty set is the set containing nothing. So the empty set is actually a subset of any other set. Okay, so the empty set is a subset of the universe. It's a subset of the A here, and so on. All right, let's look at, say, A and B. A is the set 1, 3, 5, 7, 9, and B is the set 1, 3, 5. Is there a subset relationship between these two sets? Sure. Every element of B is contained in A, right? 1 is in B, and 1 is also in A. 3 is in B, and 3 is in A. And 5 is in B, which is also in A. So we say that B is a subset of A. In fact, since B is contained in A but not equal to A, because B doesn't have 7 nor 9, we can write B is a proper subset of A. Let's see, what about D? Is D a subset of anything? Well, obviously D is a subset of the universe. In fact, any set living in your universe is going to be a subset of the universe. But what about E? E is the set of elements of U such that the element is even. D consists exactly of even numbers. So every element of D is contained in E. So we can say that D is a subset of E, and in fact it's a proper subset of E because it's not all even numbers, it's just these 3 even numbers. All right, we've talked about every set at least once except for C. Let's think about C. C is A complement. What's going to live in C? Well, let's try listing out some elements. So let's just start at the beginning of the natural number, start at the beginning of U and think about what's not in A. So 1 is in A, 2 is not, so 2 is going to live in C. 3 is in A, 4 is not, so 4 lives in C. 5 is in A, 6 is not, so 6 is in C. 7 is in A, 8 is not, 9 is in A, and 10 is not. So what do you notice here? We have that D is a subset of C, right? 2, 6, and 8. And in fact, D is a proper subset of C. What about C? Well, if you were to list out all the elements of E, and you should find that they match exactly with the elements of C. So E is a subset of C because every element of E is an even element of U, which lives in C. And vice versa, C is a subset of E. And when I get containment both ways, what does that tell me? That tells me that actually C and E are equal sets. Okay. All right, let's look at another set of sets. So A is going to be the set 1, 2, 3, 4, 5. B is the set 1, 3. And P is the set of all x such that x equals 2 to the n minus 1, where my symbol got erased. This should say n is an element of the natural numbers. All right, so I want to list all proper subset relationships between these 3 sets. So first of all, you want to get a handle on what P is. So P looks like the set of x such that x equals 2 to the n minus 1, where n is a natural number. So let's try just listing out some of the elements of P. Well, let's just go through the natural numbers. So the first element of P is going to look like 2 to the 1 minus 1. I'm going to rewrite these nicer below. So 2 minus 1 is 1. The second element is 2 to the 2 minus 1. That's 4 minus 1, which is 3. Then I have 2 cubed minus 1. So that's going to be 8 minus 1, which is 7. 2 to the 4th minus 1 is 16 minus 1, which is 15. 2 to the 5th minus 1 is going to give me 32 minus 1, which is 31. And let's just put a dot, dot, dot here. Okay, and we still got A is the set 1, 2, 3, 4, 5. And B is the set 1, 3. All right, so what proper subset relationships do we have? Well, let's just go through. Is P going to be a subset of A? Well, P has infinitely many elements, and A only has 5 elements. So there's no way that every element of P can live in A. So that's not going to work. Same idea with P and B. There's no way that P is a subset of B. So P is not a subset of anyone. Let's look at A. Is A a subset of P? And we're looking for proper, so let me actually erase the line there. Is A a subset of P? Well, let's look at the elements of A. 1 is in A and also in P, so that lives there. 2 is in A but not in P, so no. For example, there's an element of A, 2, but 2 is not an element of P. All right, can A be a subset of B? Well, same idea as we talked about before. A has 5 elements and B only has 2 elements, so there's no way that every element of A could live in B. All right, so we're left with B. B is the set 1, 3. Is that contained in P? Sure. So B is a subset of P. Is B a subset of A? Well, 1 and 3 also live in A. So B is also a subset of A. And those are our only subset relations. Okay, so we want to build up this set theory because it's sort of the foundation of what we're going to use to help teach kids math. And so here's our first application here. So let's suppose that I have 2 finite sets, A and B. If A is equal to B, then the number of elements in A is equal to the number of elements in B, and so A and B are equivalent. That means it's possible to establish a one-to-one correspondence between the 2 sets. If A is a proper subset of B, then that means that the number of elements of A is strictly less than the number of elements of B, and it's not possible to establish a one-to-one correspondence between the 2 sets. When we get to infinite sets, it's a little bit different. So here are 2 infinite sets, the natural numbers on top and the whole numbers on the bottom. So notice the whole numbers, we just take the natural numbers and tack in 0. Can we find a one-to-one correspondence between these 2 sets? Well, clearly n is a proper subset of w, right? It's not equal to w because it doesn't contain 0, but every other element of n is also an element of w. But we can still find a one-to-one correspondence between the sets by corresponding each element of n to the element of w that's 1 less than that number. So 1 corresponds to 0, 2 corresponds to 1, and so on. And notice every element of w corresponds to an element of n if I just take that element of w and correspond it to itself plus 1 in n. So this is a one-to-one correspondence. And so n and w are equivalent sets. All right, so the last thing we want to talk about is how many subsets does a finite set have? So let's try to find a pattern here in counting the number of subsets. So I'm going to start with a set P that has exactly 1 element. What subsets does that set have? Well, every set always has the empty set as a subset and itself as a subset. And here, those are the only possible subsets of P. So we have 2 subsets of a 1-element set. All right, let's amp it up a little bit. If I have 2 elements, A and B, then what subsets does Q have? Well, we still get the empty set and itself for free, but now we also get 1-element subsets, so the set containing A and the set containing B. And so I have a total of 4 subsets. All right, what if I have 3 elements in my set? So R is the set ABC. How many subsets does R have? Now I've listed them all here in front of you. Let me tell you how I thought through this. So I'm going to always start by listing the empty set, and then I just want to list all the 1 element subsets. So I get 1 element subsets for every element of my set R. Then I want to list 2 element subsets. So how many ways could I take 2 elements from the set R? Well, I can do AB, or I could do AC, and those are all the 2 element subsets containing A. So now let's move into subsets with B. I've already listed BA, so the only one left is BC. And now if I think about if I were to list 2 element subsets with C, well, it'd have to be CB or CA, which I've already listed. So those are all the 2 element subsets. And then finally, 3 element subsets. Well, my set itself is 3 elements, so I just get 1 3 element subsets. And so that's how I would go about listing out all of those subsets if I had to. So we get a total of 8 subsets. So the question is, do you see a pattern? Well, these are powers of 2, right? So I have 2, which is 2 to the 1. 4 subsets here is 2 squared, and 8 subsets is 2 cubed. And in general, if I have n elements in my set, then it's going to have 2 to the n subsets. Why is that? Well, think about the fundamental counting principle that we saw earlier. So suppose that my set has the elements 1, 2, well, I'm going to put these in quotations. 1, 2, 3, 4, all the way up to n. If I wanted to find a subset of my set of the elements 1 through n, well, for each element, I need to ask, is it in the set or not in the subset? Well, that means there are 2 choices of what can happen. So I have 2 choices. Either one is in my subset or not in my subset. And for the next element, I have 2 choices. It's either in or out, and so on. So is either in or out of the subset. And the fundamental counting principle says then if I want to know the number of ways that I could build a subset, I just need to multiply all of these numbers together. There are a total of n terms. So that means I'm multiplying 2 n times, which is the same as 2 to the n. So that's just where this formula comes from. You don't need to be able to reproduce this, but you do need to know the formula. Okay, so for example, if a set has 4 elements, how many subsets will it have? Whoops, let's go back. So if A is the set 1, A, B, C, D, has 4 elements, how many subsets does A have? Now, if I'm just asking you for how many subsets, you don't have to list them all out. And in fact, as I ask you about sets that are bigger than, say, 4 elements, that's a lot to list them all out. So I'm just asking you to give me the number using the formula. So we know that n of A is 4, since A has 4 elements. So A must has 2 to the n of A, so 2 to the 4 subsets, which is 16. All right, so in class, you're going to work on some problems, practicing some of the concepts that we've reviewed in these videos, and I will answer questions via email or in class, the following class period.